Alright, ladies and gentlemen, today we are going to look at section 7.3, volumes. As we think about the applications of the integral, certainly in mathematics and science and such, one of the major applications is that of volumes. You have learned throughout the years how to calculate the volume of various objects, the sphere, the prism, objects like that, the pyramid. But the problem is that many things in our world don't have those nice uniform shapes. Many things, in fact, are quite irregularly shaped. And to find the volume is not quite so simple as just plugging it into a little formula. So now today we're going to look at just at least a foundational look at how we find the volume of those objects. We're going to look at volume as an integral. We'll talk about square cross-sections, circular cross-sections. And then we'll look at finding other ways to find volume using cylindrical shells. Alright, we begin with just a basic outline of how to find the volume of a solid. The definition of a solid is known of known integral cross-section area A of x from A to B is the integral of that A from A to B and so on. In other words, we're talking about this formula right here. Now, what are the basic parts of this formula? Well, first of all, we do have the A and the B. Now, you know the A and the B to be the starting and stopping points of the intersected area. But this A of x is what is important. This represents a cross-sectional area of the object. And you'll see that as we go. You'll see the little boxes drawn within the areas as we go. Those little boxes represent this A of x, this cross-sectional area. And then once we have all those things put together, we do take the integral and we find the volume. Let me encourage you, though, to do number one. Number one is probably the key step. Make a sketch of what you're doing. It is so difficult sometimes to see what that cross-sectional area is if you do not have a sketch. So please take the time to make sketches on these problems. Now, of course, you know I'm going to have them for you on the notes. But as you go through the homework yourself, take time to use your calculator and make the sketches. Alright, our first example. Here we have a square-based pyramid. I'm going to move the screen down just a little bit. There we go. A pyramid 3 meters high, so 3 meters from the tip here all the way to the base, has congruent triangular sides and a square base that's 3 meters on each side, so 3 by 3 by 3 high. Each cross-section of the pyramid is parallel to the base of the square, and our job is to find the volume of the pyramid. Now, again, ladies and gentlemen, here's what I want you to think about. Now, again, we could just plug this into the formula: one-third the area of the base times the height. But let's use the integrals. Now, here's what I want you to imagine. You see the cross-sectional area right here. Well, imagine that this just represents one of infinitely many cross-sectional areas that you could draw, starting at the point here, the vertex, and going all the way down to the base. Each one is x long, x high, like this. And if we were to find the area of all of those cross-sections and then add them all up, we would then in turn have the volume of the pyramid. So here's what we have. Here is the area of the cross-section, x squared. We're going to start our first x squared cross-section is going to start at 0. You see right here 0. And it's going to go all the way to where our last one is this largest one where the base is at 3. And now we find the volume. Certainly feel free to use your calculator on these in this section, but let's work this one out by hand. It's pretty simple. It would be x cubed over 3 from 0 to 3. Plug in your numbers. 3 cubed over 3 minus 0 cubed over 3 gives me 9 cubic meters. Alright, our next example. This time we have a region underneath the curve right here. This curve is represented by 2 plus x cosine x. And we're going from there to the x-axis, and we're then taking that and we're revolving it about the x-axis so that it looks like this three-dimensional object right here. So imagine this shape right here coming out of the computer screen and then revolving back into the computer screen and then coming back, and then it makes this vase-looking shape. And we're going to go from -2 to +2. Our job is to find the volume. So again, let's imagine volume as the summation of all the possible cross-sectional areas. So if I look at a cross-section on this one, it's not a square, but it's a circle. Well, how do we find the area of a circle? Pi r squared. And if we take all the pi r squareds from -2 here, all the way up to +2 there, and add them together, then we'll have our answer. So let's think about how we're going to figure this out. Well, pi is pi, but what about the radius? Well, as we look at the radius, you see that the pink circle right here. Now that's a pretty good size radius, but if I were to move to right here, perhaps at x = 1, you see it's a larger radius. If I were to move all the way over to x = 2, you see it's a very small radius. So what is it that determines the length or height of the radius? Well, that's very simple. What determines the radius is the position of the function. You see where it dips down here, very small radius. Where it goes up there, very large radius. So we use this formula. We're going to go -2 to 2, pi, which we mentioned, and then r squared. The radius, again, is determined by the function value. So there's our function, pi r squared. Alright, I'll move my pi out, and really this one is not a good one to work out by hand. That would be quite nasty. It could be done. You'd have to expand it out, and then you'd have to do some integration by parts to break things down, which could be done. Well, let's just go ahead and use our calculator. 52.43 units squared. I'm sorry, not squared, but cubed. Alright, washer cross sections. Now this is an interesting one. We're taking a region here that's enclosed by the y-axis. You see the y-axis here. And the graphs of cosine x, which is on top, sine x, which is on the bottom. We know that because cosine starts at 1, sine starts at 0. And we're going to take this and we're going to revolve it about the x-axis to form a solid. Now, here's what you have to imagine. This is not a full shape right here. You see this cone-looking shape right here? Well, that part is actually missing. Now there's a spot that we see right here. That it's the outer edge. So this part that's on the inside, like a very deranged cup, perhaps. That's what we're looking at. But here's what I want you to think about on this one. I want you to think about the cross-sectional area. If you look at the picture here, you see in the pink, you see that what we have here is a washer. For those of you that don't know much about construction, a washer is a circle with another circle cut out in the middle. So as we look at this circle, let's think about what is going to be our cross-sectional area. Well, first of all, I look at the whole circle, including the part in, let's assume that part in the middle is filled up. Well, the radius would be there all the way up to there. So there would be my radius right there. But remember, I don't want this part right here. See, I don't, that would be what I just drew right there. But I don't want all of that. I don't want this part right here, do I? So I take that part off right there. Now, what am I left with? Well, I'm left with this circle right here with this middle part missing. Sorry, that's a pretty pathetic drawing there. But you get the idea, I hope. So how do I determine the radius? Well, if you look at the picture that's on the bottom of the screen, you have the outer radius here, which is determined by the upper function, cosine x. And we're taking away from it the inner radius, which is determined by the lower function, which was sine of x. So you see, outer radius there, take away the inner radius, and then what you have left is what we want. So when we think about pi r squared on this one, I'm sorry, before we do that, we do have to figure out where these two are equal. Sorry about that, forgot about the a and the b values. So we'll get back to the radius in just a second. So where is sine equal to cosine? Well, you know that they're equal at x equals pi over 4. Think about the unit circle. They do cross at pi over 4. They're both radical 2 over 2. So we're going from 0 to pi over 4. Now here's our radius we were talking about. The outer area, think about the whole circle, would be pi r squared, r being the outer radius, minus, and then we're going to take away that circle that was on the inside that we talked about. So that would be pi, and then there's the inner radius squared. So pi r squared, first r using the outer radius, which is cosine, minus pi r squared inner radius, which is sine. Alright, I'll move my pi out. Now you could again work this one out by a calculator if you want, but I will tell you, if you remember from pre-cal, that cosine squared minus sine squared is a double angle identity for cosine, so cosine 2x. If you don't remember that, that's okay. Again, you can just work this one with your calculator. And then we do know from last semester that the antiderivative of cosine 2x would be 1 over 2 sine 2x. So I've got the 2 on the bottom here. Remember, we had the pi out front. And now you plug in your pi over 4 and your 0. And we end up with a final answer of, move the screen down, pi over 2 units cubed. And we're having issues right now. There we go. Sorry about that. Next example, example 4. Finding volume using cylindrical shells. Now we're going to kind of change gears. You know, in these last few problems, what we've been doing is what we call the disk method. We've been finding volumes of disks. You know, pi r squared times the dx, the thickness of each one. Now we're going to change up, and instead of using disks, we're going to use hollow shells. So here's what we have. We have y equals radical x. You know what the square root function looks like. So we're going to have that. We're going to have the x-axis and the line x equals 4. So we stop right there, and we're going to revolve that about the x-axis to generate a solid. So we look at our shell right here. So imagine starting at somewhere on the function, going over to the line x equals 4. And then we take that and we revolve it about the x-axis, and as you revolve it, you get this shell. Now imagine that shell, and imagine another shell inside of it, and another one inside of that, and another one inside of that, until we get down here to the x-axis. And then imagine another shell outside of this one, and another one outside of that one, all the way up to here. Now, they are getting wider as we draw them this way, and smaller this way. But then as we draw them going this way, where they're getting wider, notice that they're also getting shorter. And then even though these are becoming narrower, they are getting longer. And so our job is to find the volume. So how do we find the volume of a cylindrical shell? Well, how do we find the area of this wraparound portion? Well, that area would be the lateral area of a cylinder. And if you know how to find the lateral area of a cylinder, that's 2 times pi times radius times height. So 2 times pi times radius times height. Notice that we are going dy on this one, because as we are drawing these, you see we're moving up and down. And so we're talking about a delta y thickness here. We're going from 0 all the way up to the highest y value 2. Well, again, we ask ourselves these questions. What determines the r? What determines the h? Well, first of all, what determines the radius? The radius is just some value up that we will go. So maybe I go up this high, maybe this high, maybe that high, and so on and so on. But what determines the height? Well, the height is an interesting one, because the height is the distance between this line right here, which is x equals 4, and the function here, which is x equals y squared. And you think about this, if you were to solve this for x equals y squared. So it's that distance there. So we subtract, to find the height of the cylinder, we subtract this line minus the function, which is what we have here. Now we can pull the 2 pi out, and we can distribute the y. That would be 4y minus y cubed. And then we can take the antiderivative and then plug in our numbers, and we have 8 pi units cubed. Now, ladies and gentlemen, we're about at the 15-minute mark, which means this video is going to stop. So I'm going to stop at this point, even though we are almost done, and we'll resume the next slide in the next video.